Okay, guys, hope you're enjoying your snow day. Unfortunately, we can't take a break from chemistry for this week because we don't have any snow days built in. And for us to get to the end of Module 16 by the end of the year, we really need every week. So unfortunately, you guys need to keep moving right along with your syllabus. This module, Module 8, will be due at our next meeting, so next Monday. So uh, as you're listening to this video and watching this video, would like you to have your periodic table in front of you because I'm going to reference the periodic table a few times and that'll make it easier if you have it right in front of you. So if you guys recall, last week we talked about ionic bonding and how an ionic bond is formed. And if you remember, an ionic bond is created from a metal and a nonmetal. So that would be one element from the left-hand side of the periodic table and at least one element from the right-hand side of the periodic table. If there is a metal in there at all, it's considered an ionic bond. And if you recall, we talked about last week, that it actually takes a transfer of electrons for that to happen so that your metal becomes positive, your nonmetal becomes negative. And because of that, when those types of compounds are dissolved in water, they conduct electricity. So this week we're going to talk about covalent bonds, and covalent bonds are a little bit different. First of all, they do not conduct electricity when they're dissolved in water, and covalent bonds are made of any of the nonmetals. So it's the nonmetals, all the ones on the right side of the periodic table or to the right of the stair steps. Now hydrogen is a little bit unusual. Hydrogen, even though he's to the left of the stair step, he goes back and forth. He acts like a metal sometimes and non-metal sometimes. So if it's hydrogen and one other nonmetal, or hydrogen and a couple other nonmetals, you're going to consider him a nonmetal, and he's going to be doing a covalent bond. Now, in covalent bonds, it's a little bit different, that these guys share electrons. So let's look at an example dealing with chlorine. Okay, so if you look on your periodic table, chlorine is in group 7A. So that tells us chlorine's going to have 7 electrons around him for his Lewis structure, or his electron diagram. So because he's a nonmetal, chlorine is going to want to take on electrons. So, and if you recall last week, we talked about that elements spend their entire life trying to get 8 valence electrons, either by losing electrons or gaining electrons. And so chlorine spends its entire existence wanting to be just like argon, because argon has 8 valence electrons. And if you remember, chlorine is a homonuclear diatomic, which means that if chlorine can't find something else to bond with, it's going to bond with itself. So chlorine bumps into another chlorine atom. And I'm going to just erase this guy for right now and add him over there. I just did some maneuvering just so that you can see this. So chlorine meets another chlorine and they bump into each other, and each of them go, wow, I really wish I had 8 valence electrons. Don't see anything else around, but chlorine says to the other chlorine, hey, what if we were to share these electrons? That they would spend part of the time with me and part of the time with you. And if they share those electrons at any time, that means that they're going to have 8 valence electrons at least part of the time, and that's better than nothing. So chlorine likes that. So let me get rid of this. And so what they do is they do get this partnership where they share the electron. And when they do that, they create a bond. And we show a covalent bond by a single line. And that means that they're sharing electrons. So if we look around the outside of each chlorine, we've got 2, 4, 6, 8. If you count the sharing one, 2, 4, 6, 8. Both chlorines are happy. This is called a single bond for a covalent compound. So let's see how this works for a bigger compound. Let's look at CH4. Okay, so carbon, if we look on our periodic table, carbon is in group 4A. So that tells me that carbon has 4 valence electrons. We already know hydrogen is in group 1A and it has 1 valence electron. And we're actually going to need 4 of these. I am just randomly dispersing these around that carbon. Okay. So carbon goes, look, we can share this electron, we can share these, we can share these, and we can share these. Carbon's now happy because it's sharing 4 more electrons, so that gives it a total electron count of 8. Hydrogen's happy. Remember, hydrogen really doesn't want to get to 8. He wants to get to 2 because he only has the 1s level, and s orbitals can only hold 2 electrons. And so carbon shares the shares the electrons with hydrogen, and that's our Lewis structure for CH4. So if you look on page 267 in your text, you're going to see some rules for constructing Lewis structures. Remember, you can't subtract or add any extra electrons. You have to deal with what the number of electrons you have, and your ending number of electrons has to be the same as your starting number of electrons. So let's look at another example here. Let's look at oxygen, because oxygen's another one of those, if you recall, it's a homonuclear diatomic. So oxygen is in group 6A. Oxygen has 6 valence electrons. Now I'm drawing one a little bit backwards just because I want you to see where these guys can share. So oxygen really wants to get 2 more electrons so that it can be like neon. If it had 2 more electrons, it'd be really happy. So oxygen bumps into another oxygen and it goes, hey, what if we share those 2 and we can share those 2? Then that way, at least part of the time, each of us have 8 electrons orbiting around it in our valence shell. So we end up with a Lewis structure that looks something like this. So we end up with 2, 4, 6, 8, 2, 4, 6, 8 electrons around each of them. And the 2 lines in the middle, or the 2 lines here, that's our double bond. Okay, just like the other one had a single bond where you were sharing 1 electron pair, a double bond is going to share 2 electron pairs. So oxygen's now happy. We can even get a triple bond. If we look at nitrogen, nitrogen is in group 5A. Nitrogen's going to have 5 electrons. And once again, I'm drawing these a little backwards just so you can see how these work out. But nitrogen can share that pair, they can share that pair, and they can share that pair. Or the Lewis structure looks like this. And if we count these, we'll see 1 set, 2, 3, 4. 4 times 2 is 8. 2, 4, 6, 8. That one's happy too. We have this bond in the center here, that's a triple bond, and nitrogen's now happy. Okay, so we can have single, double, and triple bonds. So once you think about it for just a second, of the 3 bonds, which do you think would be the most difficult to break? Single, double, or triple? Okay. If you think about it, it makes total sense. The triple bond would be the most difficult to break. It'd be like having 3 strands of thread rather than 1 strand of thread. 3 is going to be harder to break than 1. So it takes more energy to make a triple bond than it does for a double bond. So let's look at a couple of examples here. First one we're going to look at is NF3. Let me switch this back to black here. Okay, so using our rules on page 267, I'm going to start with my nitrogen here. I'm going to put him in the center. 1, 2, 3, 4, 5. I'm rearranged the electrons just in the Lewis structure, just to make it a little bit more clear. As long as you have 5 around it, you're good. Okay. Now, if we look at fluorine, fluorine is in group 7A, so that tells me that we've got 7 electrons in its outer shell. So I'm going to put one here, I'm going to put one here, and I'm going to put one here. You'll notice I kind of lined up those single electrons just to make it a little bit easier. So you can see nitrogen's looking around. He goes, I really need 3 more electrons, and that will give me 8. Fluorine's looking around going, if I just had 1 more electron. So they're gonna share. If they share those two, and share those two, and share those two, then we end up with a Lewis structure that looks like this. And everybody is happy. If you count them all, everybody's got 8 electrons in its outer shell. We've got 3 single bonds here. So let's look at another one. This one's a little bit more difficult. We've got CCl2S. Okay? So whenever I see a compound that has carbon in it, I always put carbon in the center, just because I know carbon is in group 4A, and so carbon has 4 valence electrons, and he's got more that he's gonna want to share. Okay. Now chlorine, we've got 2 chlorines here, Cl2. Chlorine is in group 7A, so that tells me he's got 7 valence electrons. And then we've got sulfur, and I'm going to put sulfur up here. Sulfur now is in group 6A, just like oxygen, and so he's got 6 valence electrons. So carbon is able to share those 2 electrons with chlorine and those 2 electrons with chlorine. But carbon still needs 2 more electrons. At the same time, sulfur needs 2 more electrons. And if you look here, they could share these 2 and they could share these 2. And if they did that, then we end up with a Lewis structure that looks something like this. Okay. I just want to get rid of that guy right there. That's just a... Okay, so we end up with this Lewis structure where carbon does a single bond, here's a single bond here to the chlorine, another single bond here, but it's got a double bond to the sulfur because it's sharing those 2 electrons. Okay, so if we do a count on our electrons, we start it with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, and then if I count here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 12, 14, 16, 18, 20, 22, 24. Okay, they both match. So I am going to be sending by email a practice sheet for you guys on covalent bonding electron dot diagram. And this would have been done in class today as a lab. It's front and back. So we will briefly go over it on Monday before you turn it in, but at least attempt it to make sure, get some practice in with doing these covalent bonds. And if you guys have any questions at all, you can just shoot me an email. And otherwise, enjoy the snow. Hope everybody's getting out to wintergreen. And I don't want to see any broken arms or legs on Monday. Take care. Bye.